Thank you everyone for coming. I know it's been a long day. My name is Jenson. So today I'm going to talk about advanced material handling using this new Sony Timeofflight technology and also what our 3D ToF product is. So to start, I want to just talk a bit about 3D sensing in general. There are a lot of 3D sensing applications out there on the market, and they're used in different industries, ranging from both industrial, like pick and place, pallet depalletization, or warehouse robots and metrology. And there are also like consumer ones like drones, as well as safety and security like people counting and patient monitoring. So all these different applications all use 3D sensing, but they use different types of 3D sensing. There's no one type of technology that can be used and solve issues with all of these applications. So today, the technology I'll focus on will be more towards stereo vision, time of flight, and structured light. I'll be comparing some of them and see how they are being used in materials handling. So to just give a brief overview of how these technologies work, stereo vision works by using two cameras that are a fixed distance apart, and they capture the same scene. And they determine the depth information by matching features in both images to extract what's called disparity. And using that disparity information, they can calculate the distance of the object. But it suffers from one issue called occlusion, where if one of your objects is only seen by one camera, then you can't do the matching and you can't calculate the distance. So example of such a product is the Intel RealSense camera. So what I just described earlier is called passive stereo vision. There's also active stereo vision, where you use a light projector to add texture to the scene. So with stereo vision, for example, if you're imaging something white or just a white wall, there's no texture. So it's very hard for the algorithm to match features within both scenes. So they use projector to add more texture into the scene, so it improves the matching algorithm. And then the structured light, which uses a structured light source with a single camera. So the difference between a structured light and active stereo is that active stereo doesn't really care what kind of light source you're using. It just wants more texture in the scene. How structured light works is that it projects a known pattern. It knows what the pattern is supposed to look like. It projects it onto the scene, and based on what object you're looking at, the pattern would deform, and it uses the deformation to calculate the depth data. So for structured light, it needs to be calibrated. It needs to know what the pattern is supposed to look like. So structured light typically are used in more higher-end like metrology applications because the accuracy is typically much higher than stereo vision, for example. But the resolution of structured light is limited by the pattern it can project from the projector. And there's also time-of-flight technology, which uses a different type of techniques. So stereo vision and structured light both uses triangulation to figure out the depth. Time of flight, like its name, measures the time that it takes the light for emit and bounce back from the object itself. So there's two ways to measure this time. One is directly measuring the time, and one is indirectly using the phase difference. So this is known as direct time of flight and indirect time of flight. But with time of flight, sometimes you don't know exactly where the light could bounce back, but it can come back in different paths depending on how complicated your scene is. So something can appear further than it actually is. So this is a phenomenon called multipath. Typically, time-of-flight cameras are less expensive because there's less calibration needed compared to the other 3D sensing technology. So example of this is Microsoft Connect 2. So Connect 2 is actually used quite often as a baseline for comparison in a lot of the academics papers because of its performance in terms of time of flight. So if you were to sort of segment and try to sort of understand how all these different 3D sensing applications, how their requirements differ from each other, you can start off by sort of having this graph here. You have your applications that require high working distances. So like navigation, people counting, obstacle avoidance, and mobile robots. So they want large working distances, and they don't care as much about accuracy. You want to know that whether an object is there, whether the size is off by a centimeter or not, really doesn't matter to you because your robot needs to avoid it quite early on anyway. So in the middle, you have automated materials handling, where you're typically operating maybe 1 to 3 meters apart, and you would want to know a bit more accurately about the size of the object you're picking up, so you can accurately pick up the object. So the accuracy needed is about 1 to 5 millimeters. And then you have your higher end application like inspection and metrology, where you're being using manufacturing lines or reverse engineering, and you want to know the size of that, the object you're looking at, down to like a micrometer level. So for us, our product will be focused on automated materials handling. So in materials handling, currently there are many challenges. Number one being sensitivity to ambient light. So even though warehouses are indoors, there are windows or doors that open and close, so the sunlight gets introduced, and that creates a problem when it comes to 3D imaging. There's also a lot of different packaging that products are being packaged with. There are more shinier materials or clear materials, or ones that reflect light a lot. So that again causes problem with the 3D data that they capture. Some systems require in-field calibration. So for example, when the light source heats up, the pattern is projected could slightly shift, and that could affect the 3D data that you're calculating. And a lot of these 3D sensing cameras out there, they don't calculate the depth data on the camera. The raw data is taken off the camera, and they need to calculate it in real time on the host. So again, that takes a lot of CPU resources. So when we compared the three technology, working distance for stereo vision and structured light are both limited by the baseline. For example, in stereo vision, as the target gets further away, it's become harder to match the features. You'll need a larger baseline in order to match it better. But with time of flight, the distance, the working distance itself is scalable. You simply need more light in order for more light to bounce back and get a better data. In terms of depth accuracy, structured light provides the highest depth accuracy, with stereo vision, passive stereo vision being the lowest. In terms of depth resolution, stereo vision, as I mentioned earlier, is sort of limited by the scene. If it's a complete white wall, you can't really match anything, then your depth map resolution is very limited. So it's the actual resolution you can get out of the stereo vision is limited by the texture of the scene. For structured light, it's sort of similar. It's limited by the pattern of the resolution of the light pattern. As for time of flight, you can fully use the resolution of the image sensor. Some technology like stereo vision and structured light requires some in-field calibration, whereas time of flight doesn't. And size is sort of similar to working distance. So as your working distance increase, the baseline has an increase for stereo vision and structured light, so the size of your camera increases. While time of flight can maintain a very compact size. In terms of cost, stereo vision has been around for much longer, so it's typically lower cost, whereas structured light requires highly calibrated components, so the cost is typically much higher, whereas time of flight fits somewhere in the middle. So for us, we use a new sensor from Sony called this technology called Sony DepthSense. So it comes from a company that they acquired called Soft Kinetics in 2015. So the Soft Kinetics company made time of flight technology. So what Sony did was to combine this time of flight technology with their own sensor technology, which is called backside illumination. So what this does is that they can create a time of flight sensor that has better light collection efficiency compared to the other sensors on the market. So what this means is that they can make this pixel smaller without sacrificing performance. And as a result, the sensor can become smaller and they offer higher resolution. So the sensor that we're using is called IMX556. It's a half-inch sensor offering VGA resolution and 60 frames per second. So our product is being demonstrated today at our booth. So the image on the left here is a prototype that we're showing. The actual product will not look like this. It will be similar in size, but it will not have exposed PCBs in the front. So the camera offers 640 by 480 depth resolution at 60 frames per second. In terms of precision, we are measuring at a distance of 1 meter, about 2.5 millimeter. So this is also known as sigma or repeatability or Yeah, or standard deviation. So you see different naming conventions in different product data sheets. So the goal of us offering this product is being able to offer the same kind of 3D performances that some customers are already having without having to pay more. So this is the preliminary specification of our product. In terms of operating modes, we offer 3 for 3 different working distances, at 1 meter, 3 meter, and 6 meter. And accuracy, so far, some of the preliminary data that we measure are mostly limited to 1 meter. So for accuracy, we're getting better than 5 millimeter at 1 meter distance. And precision, as I mentioned, is 2.5 millimeter. And the field of view is 65 degrees by 46 degrees. Our product will also be GeniCam 3D compliant. So customer can just directly use our camera in a lot of the existing 3D softwares out there, like MVTech or Matrox, for example. So the 3D pixel format is already defined by GeniCam. The camera will also work in our SDK called Arena. So customer can control and acquire images using the SDK, as well as some visualization tools such as point cloud, depth map, and confidence map. So in order to understand what kind of performance we can get out of the sensor with this preliminary measurements, so this is EMVA data that we captured. So what we want to emphasize here is that the QE at the wavelength that we're using for our laser diode, which is 850 nanometer, the QE is actually pretty high. So using this EMVA data, we sort of did some simulations to understand what kind of performance we can get out of the sensor. So this blue line right here is sort of our modeled result based on 80% modulation contrast, 82 electron read noise, and 10-bit quantization of the data. So the red dots here are actually the performance that we measure from the camera. So we're actually hitting the theoretical maximum that we think we can hit using the sensor. What this also shows is that on the x-axis, you have more electrons. So as you collect more light, your precision isn't getting any better. You're sort of flattening out at about 1 millimeter. So what this means is that in order to improve that performance even more, you would potentially need a much bigger pixel. So using this data, we've also calculated some more precision data based on the following test conditions. So this is in a dark room using 4 lasers and at exposure time of 1,000 microseconds. So what we're showing here is that at a distance of 1 meter, we're getting a precision of 2.5 millimeter, meaning when you measure the data, you can accurately, your data is precise to a range of 2.25 millimeter. And at 2 meters, we're getting about 4.56. There's also spatial precision, which is slightly different from temporal precision that's shown earlier. Temporal precision is about if I measure 100 frames over time, how much of a shift am I expected to get? So earlier it was about 2.5 millimeter. Where spatial precision is, doesn't matter what pixel on the sensor I'm measuring from, what kind of variations can I expect? So again, at about 1 meter, we're getting 2.5 millimeter precision as well. So all these are preliminary data that we measured, but we plan on improving this in our final product as well. And the following is accuracy measurements that we've done, which tells you if my object, for example, is only 10 centimeter, how accurately can I actually measure this? So for us, at different distances, we get about different accuracy, but it's within plus or minus 5 millimeters. And as I mentioned earlier, Connect 2 is sort of the baseline a lot of people measure their ToF performance to. So on the right here is a picture of a female coworker that we took. You can see on our image, the features such as like the nose and the neck is much more clear compared to the data on the Connect. And these are some more sample images that we took of different objects. So this is sort of like a few chocolate muffins that we put on a box. And you can see from the depth data, you can even see the chocolate chips that's on the muffins themselves. And these are boxes that we stack at different depth. So it sort of allows you to see what kind of different distance that you see and the features of the box. And then these are some PVC pipes that we taken an image of, where you can see that the image isn't distorted, and from the point cloud you can actually see there's a little defect on a little point right on the pipe that you can see via this is only like a 2-3 millimeter wide defect on the pipe, and it can be seen in the point cloud image. So if you want to see our demo, please come to our booth. And just to wrap up, I just want to talk a little bit about who we are. So our company is called LUCID Vision Labs. We were established last year in 2017. So we're based in Vancouver, Canada, where our sales support and engineering and manufacturing is located. We also have sales offices in Canada, Germany, and China. Right now we're about 50 people, and we look forward to seeing you at our booth to answer any questions or see any live demos. Thank you.